Welcome back. So you remember a couple videos ago we came up with eigensolutions that we had for this matrix equation x dot equals ax. And when we did this, we found there were some eigenmodes, which you can see on my second line right here. And those eigenmodes each had a different S1, S2, or S3. And there were n of them, one for each dimension in the x vector, and each dimension in the x vector is another state variable. So we found a very interesting situation where we could find an uncoupled system, and each of those eigenmodes, the amount that we had in our actual solution, was denoted by these c's you see on the second line in the c1, k1, e to the s1t. The c1 tells you how much of that eigenmode you have, the c2 tells you how much of the second eigenmode you have, and so on, down to the last one. And so if all the c's except c1 were 0, then you would only have the first eigenmode. And that means that in this reference frame with the c's, it's like we're in a new set of state variables that has everything uncoupled. So when I start one eigenmode, it just remains in that eigenmode and I never get the other ones. So let's look at if we could actually do this for not just at t equals 0 to find the c's. Could we just completely move into that new coordinate system that would have these eigenmodes? Like, for example, with the pendulum that you watched in the last video, there was one where it was the difference in the angles and the sum of the angles. And those are the two uncoupled eigencoordinates. And how could we get there? So last time we discovered what we have in the last red line here. We discovered C or Z, which might be this new uncoupled thing, looked like it could be written as T inverse times X. And T inverse was the matrix of the eigenmodes, all put next to each other and inverted. So let's just see if we can make that work. So if we start out from the eigenmode equation that we have here on the second line, or the first line in blue, we could rewrite that as T. Notice that it's got all the k's there. Those are the first thing in the in each of the terms of the eigenmode equation. So I've got k1 times e to the s1t, and that gives me, or actually multiplied by c1. So if you just take the second two matrices here, you'll have c1 times e to the s1t if you do this matrix multiply. And then if you multiply this combined matrix here with the t1, you certainly get what we were hoping we would get. You're getting x equals t times z. And that actually gives you, if you invert the t, you get z equals t inverse x. So now we can go back and forth between this uncoupled system and the coupled system. And that's really handy. Furthermore, we have a matrix here which is square that has e to the s1t, e to the s2t, and so on, all the way down the diagonal. And, you know, it makes me wonder if we could make a thing that was taking the exponential of a matrix. So how in the world are we going to do that? Well, the only thing I know how to do with matrices is multiply. I know how to take the inverse of a matrix. I know how to add matrices. And that's it. I don't know how to take the exponential of a matrix. But I do remember a thing we learned back in calculus. And that thing was the Taylor series here. If you look at the top line in my notebook right now, you will see that the Taylor series for e to the st is 1 plus st plus s squared t squared over 2 factorial plus dot dot dot. And all of those operations I could actually do with matrices. So what if I said this matrix back up here maybe this guy right here was e to the dt, where d was a matrix that looked like this. It would have S1, S2, dot, 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 down to Sn, and all zeros up here and all zeros down here. And if I was to try and do e to the dt, would I get this matrix up here on the second line right here? So let's go look and see if we did that. So if I did e to the dt, it would be the identity matrix, which is like 1, and then plus dt, d being a matrix, times t, which is a 1-by-1 scalar quantity, and then I've got d squared t squared over 2 factorial. And if you actually work that out, you will find out that sure enough, you get this matrix right here with those Taylor series for each one of the exponentials, which means that at least it works for this diagonal matrix. And notice that we had this transformation that would take us from the uncoupled coordinates to the coupled coordinates x. And the uncoupled coordinates were z, and if we do that, we can actually transform the initial equation x dot equals ax. We can transform it into an equation z dot equals t inverse a times t times z. And that looks just like the x dot equals ax, except it's now z dot equals actually d times z. D is this big matrix with all the s's down the diagonal. And I'm leaving you with a little bit of an exercise here. First of all, can you show that d is t a t inverse? That should be pretty simple. And then a little more challenging is show to e to the at, where a is the original A matrix, is equal to t e to the dt times t inverse. And a little hint for you there, use the Taylor series, and you will find out that you'll have a bunch of t times t inverses in that Taylor series, and you can cancel a t times t inverse because that's the identity matrix. And anything multiplied by the identity matrix is the same matrix you started with. So it will actually make it pretty easy to come up with this formula we have for the exercise here. And it will show you that it actually follows the same definition we used if we call the Taylor series our definition for e to the at. And so now we actually have a new way of solving x dot equals ax. We can say the solution x of t equals e to the matrix a times t times x at the initial time, x0. So now you have another method of solving this equation.